All right, so welcome back. We're going to do a little bit more discussion about complex impedance. Just to remind you what we talked about last time, we introduced this idea of impedance being the ratio of the complex input voltage and the complex current. Right? We talked about what it means for a voltage and a current to be complex. It's just that the real part of that is the actual physical thing. And we saw that a resistor has a complex impedance that is simply the real number R, the resistance, which means that the current is always just directly proportional to the voltage with the proportionality of R. And we also saw that a capacitor is actually different when you go ahead and you find what the impedance of a capacitor is. The impedance of a capacitor is 1 over j omega c, right? And the way that we interpret that is actually that number, 1 over j omega c, tells you both how big the voltage is in the current is relative to the voltage, or the voltage relative to the current, but also tells you what the phase difference is. And in particular, in the case of a capacitor, the voltage lags the current by pi over 2. And that's why you have this 1 over j here. This 1 over j is equivalent to an e to the minus j pi over 2, which says the voltage lags the current by a phase of pi over 2. Okay? So those are the sort of fundamental ideas. And what I want to do in this video is extend those a little bit to actually go through the example of a low-pass filter using complex impedance ideas. Okay? So here's our circuit. We've got a sinusoidal input that's at some frequency. So we'll make that be a complex voltage, V naught e to the j omega t. And we're going to pass that through a resistor first, R, and then through a capacitor, C. Okay? And our output voltage, I'm going to measure across the capacitor. Okay? So here's the nice thing about complex impedance. We could take this and turn it into a differential equation and manipulate that differential equation and do all kinds of integrals and stuff. Or we could simply say, you know what, I know that in this circuit I've got linear circuit elements, so the resistor is going to be sinusoidal, is going to have some sinusoidal voltage across it, the capacitor is going to have some sinusoidal voltage. I know what the impedances are, so I can actually do this using complex impedance, which turns out to be a much easier way to do it. Okay, so here's how I'm going to do it doing complex impedance. The first thing I'm going to say is I'm going to assume there's some current in the circuit, and I want to find that current, right? So the way I find that current is by using KVL, right? So I'm going to add up the voltages around the loop and say I know that the voltages around the loop have to add up to 0, right? So what are the voltages around the loop? Well, I've got V naught e to the j omega t. That's going from here to here, right? So gone up. Now I'm going to go down across the resistor. So that's going to be minus I times R, right? And then finally I'm going to go down across the capacitor. Well, the impedance of the capacitor we found was 1 over j omega c. So the voltage drop, the complex voltage drop across the capacitor is just going to be I divided by j omega c.
Can you pause here for a moment? Like, I understand the first part, IR,
Yep.
but like the...
Well,
yeah,
and so in general, the sort of idea of impedance, right, is that the voltage across any circuit element is the impedance of the circuit element times the current through the circuit element. Okay, so in the case of a resistor, right, this reduces to V equals IR. Right? In the case of a capacitor, the voltage across a capacitor is 1 over j omega c times the current through the capacitor, right? Which tells me, and this is always assuming a sinusoidal voltage and a sinusoidal current, what this tells me is that the voltage across the capacitor is pi over 2 behind the current, and that the magnitude of the voltage is 1 over omega c times the magnitude of the current. Okay? Yep. So it's actually the same thing as a resistor, except that it also, the fact that it's complex, embeds this phase information. Okay? Is that cool?
Yeah.
All right. So as I go around the loop, all those things added together have to come out to be 0. Right? So, okay, now this is just an algebra problem. Right? I can now solve for I. And if I solve for I, what am I going to get? Well, I'm going to bring V naught over to that side, or this crap over to the other side. I'm going to do some algebra, which I will not even try to do out loud. I will just do it. Right? Do you buy that? Right? I took this stuff over this side, so I've got I times R plus 1 over j omega c. Then I just divide.
Yep.
Okay? So what does this actually mean? Well, if I look at this, my current actually is some number up front, right, that tells me what the phase and what the size of the current is times e to the j omega t, right? So this stuff out front is kind of the important stuff with regard to understanding the current. It tells me how big it is, and it also tells me what its phase is. So let's take a second to just look at this current before we go on to figuring out the actual filter aspect of this. So how does this behave when omega is small? And when I say omega small, what I mean is that this term is small enough to make this term be large relative to this term.
So it basically behaves like,
When omega is small, this term is going to dominate, right? And so what I'm going to end up is I is equal to V naught divided by 1 over j omega c.
yeah.
Okay? So in other words, the current is mostly going to depend on what the capacitance is, right? So mostly I'm going to be limited by this capacitor,
Yep.
and the current's going to be out of phase with the voltage because you can see I've got this J running around here. In fact, if I rewrote this, I would get J times V naught over times omega. Sorry, I'd get J times V naught times omega times C, right? Which is actually consistent with what we found last time.
Yeah.
Okay. What about when omega is large?
Then R will dominate the
So then R will dominate. This will basically go away, and I'm going to get a current that's V naught e to the j omega t. I should have had an e to the j omega t here too. Divided by R.
Yep.
Right? So it's just going to look like a resistor, right? So at large values of omega, this capacitor basically is just a short, as we talked about earlier. At high values of omega, at low values of omega, this resistance is relatively unimportant, and most of the voltage drop will be across this capacitor. Okay, so we figured out what the current is. If we want to actually figure out how to think about this as a filter, though, we actually need to figure out what V out is, right? So what's V out? Well, I know what the current is, right? I also know what the impedance of the capacitor is, right? So the voltage across the capacitor is simply the impedance of the capacitor times the current,
Yep.
right? So I'm going to have J times omega, 1 over j omega c, right? That's the impedance of the capacitor, right? Times the current. Well, I know what the current is. It's V naught times e to the j omega t divided by R plus 1 over j omega c.
Yep.
Okay? In other words, V out over Vn, right? And if I assume that V out is going to be also sinusoidal, right? I could also say this is V out e to the j omega t, but the ratio of V out to Vn, right, is equal to 1 over j omega c divided by R plus 1 over j omega c, right? Because I'm just dividing through the V naught, I'm dividing out the e to the j omega t because there's going to be an e to the j omega t.
So this is just
sides.
algebra, right?
So this is just algebra, and all that this is telling me two things. In the same way that the impedance is telling me what the size of the current is relative to the voltage and what the phase of the current is relative to the voltage, this term, the gain of the circuit, is telling me what the size of V out is relative to Vn and what the phase of V out is relative to Vn.
Okay.
Okay, you buy that?
Yep.
All right, so let's take a look at this for a second, and I'm going to multiply through to clean up. Let's just clean it up a little bit. So let's multiply the top and the bottom by j omega c.
Yep.
Okay, so I'm going to get V out over Vn. Well, if I multiply the top and the bottom by j omega c, what do I get? I get 1, right, divided by R times j omega c, right,
Plus 1.
plus 1. Okay, so that's what the gain of this circuit is, right? So what happens if I plot the magnitude of that as a function of omega?
So for really small omega, it'll be just 1.
Yeah, for really small omega, this term is going to basically be 0.
Yeah.
So it'll basically be 1, right?
And for really large omega, it'll be basically like 1 over a really high number. So
So, and if you think about how it's going to behave For really large values of omegas, this term will dominate this. So it's basically going to go, the size of it, right, for large omegas, it's approximately going to be 1 over j times omega times r times c.
Yeah.
Right? So the magnitude of this, it goes as 1 over omega rc. Right? So it's going to stay at 1 until the point where omega is approximately rc.
Yep.
Right? Or 1 over rc, sorry. 1 over rc, not rc. Right? And then once I get to that frequency, above those frequencies, it's approximately going to roll off as 1 over omega. Right? So above that, it'll basically behave like 1 over omega, or 1 over omega times r times c. Right? So this is what when you plot this as a logarithmic plot, right, you get a Bode plot. Right? This is omega to the minus 1. This is constant omega, so your Bode plot is basically those two things put together. Right? If I plot what the phase is of V naught over Vn, or V out over Vn, what does that look like? Well, if I come back up here, when omega is small, this term is basically 0. V out is directly proportional to Vn, right? It's actually got a phase of 0, right? Which means that the output voltage is directly following the input voltage, right? So right, here's my omega equals 1 over Rc, right? By the time I get to omega equals 1 over Rc, what's the phase here? Well, now I've got 1 over j plus 1, right?
Yep.
And that actually has a phase of minus pi over 4. And I'll ask you to kind of believe me on that.
Okay.
But if you think about j plus 1, right? Here's j plus 1, 1, j, right? So j plus 1 has a phase of pi over 4, right? 1 over j, I'll get a negative phase out of that because I could rewrite this. I could rewrite j plus 1 as radical 2 times e to the j pi over 4, right? So you buy that?
Radical
So
2 is the
length of 1, so this radius
That's
is radical 2,
and the angle
is pi over 4,
Yeah.
right? So then 1 over j plus 1 is 1 over square root of 2 times e to the minus j pi over 4.
Yeah.
Okay, so at the angle, at the frequency 1 over Rc, this should go to a value of minus pi over 4, right?
Okay.
And what happens as omega gets really large? Well, if I come back up here to this expression, when omega is large, I have big number times j plus 1.
Yeah.
So I basically have 1 over j,
1
over a big J. So what's the phase at that point? So the phase of 1 over 10,000 j plus 1 is what? What's the phase of
Yeah, what is-
10,000 j plus 1?
Well, going a little bit back, what exactly is phase? What?
Okay, so
Yeah.
phase is, so there are two answers to that. One is, we're just talking about the angle of the complex number is, so
Okay.
where it's sitting in the complex plane. That's one answer, and that's the first answer I want to get to
Yeah.
here. So if I look at this,
That's a like complex
Right.
plane
so
triangle.
if I were to plot the point 1 over 10,000 j plus 1 in the complex plane, where would it sit? Well, 1
Close
over,
to 90.
so 10,000 j plus 1 would sit very close to 90,
Yeah.
right? Therefore, 1 over 10,000 j plus 1 would actually sit very close to negative 90.
So negative pi over 2.
So negative pi over 2. Right? So as I get to very high frequencies, I'll asymptotically approach negative pi over 2.
Yeah.
Okay, so that's one interpretation of phase, is just it tells me what angle the complex number is at. Right? A second interpretation of phase is that it tells me what the relationship is in time between the input voltage and the output voltage. So here, right, we have a phase of 0 and we have a magnitude of 1, right? So what that means is if I were to plot V out and Vn, right, Vn would look like this, and V out would look identical,
Yeah.
right? Because the phase is 0, right? So they're in phase, and the magnitude is 1, they have the same size,
Yep.
right? When I come over here, on the other hand, right, Vn looks like this, right? But V out lags Vn by pi over 2, right? So this is the point pi over 2. So while Vn peaks right here, Vout is not going to peak until here, right? And furthermore, Vn is way, way smaller than, Vout is way, way smaller than Vn. So now what that's going to look like is something kind of like this, right? It's going to peak there, it's going to be 0 there, it's going to peak again there, right? So Vout lags Vn, right? It's later in time. It reaches the peak, this peak later than this peak, real out to Vn, and Vout is smaller than Vn. So when we talk about phase, we're talking about whether it's lagging or leading, and when we talk about magnitude or gain, we're talking about whether it's bigger, smaller, or the same.
Yep.
Okay, does that make sense? Right. So this is how you would sort of use these ideas to figure out, one example of a filter, right? So this is just a simple RC filter. But one of the sort of nice things about this formulation is now you can start to look at circuits like this and say, well, let's see. I've got a resistor that has constant impedance. I have a capacitor that has impedance that gets smaller as frequency goes up. So what happens to this at low frequencies? Well, low frequencies, most of the voltage drop is going to be here. At high frequencies, most of the voltage drop is going to be here. This is a low-pass filter, right? So I'll give one other sort of filter example for the sake of arguing. Actually, will I think I won't. We've been talking for 16 minutes. Let's call it quits there. So hope you found that useful. And as always, comment on our YouTube page or whatever. I guess that's what you say, right?